All right, so welcome back. Last class we had our first test. I've graded about halfway through the tests. It doesn't mean I've finished grading anybody's. It means I've graded half of everybody's tests. So unfortunately, I don't have them to give back to you today. If you don't want to wait until after spring break to get your grade, send me an email and I will email you your grade as soon as I have it. Please send your email from your GCC email address. If I get something from QtPie1995, I'm not going to respond with personal information, even if I know it's Tim's email address. Like I'm not going to respond. So send it from your GCC address. So we've got two topics for today. One of them is probably something quite familiar to you, the Pythagorean Theorem. And then we're going to talk about laws of exponents. The Pythagorean Theorem stuff will be much shorter than the laws of exponents piece. So most of today is laws of exponents. And then again, this is our last class before next week off for spring break. So we'll go to Alex for number one. Thank you. Alan, number two. Okay, so let's think about this. So we got that picture right there, and Boggs is over at third and throwing to first. So I'll draw a line on here and say basically we're trying to find the length. Let's see, where's third base is here. We want to know how long that thing is. Yeah. Anybody happen to know any facts about the baseball diamond? I think 90 is important, but I don't think that's how far it is from the pitcher's mound. I think 90 is somewhere else in this picture. Morgan? That's right. So each of the base paths is 90 feet long. So for example, here to here is 90, and also here to here is 90. Okay, and so we need to know that in order to answer this question. If you take a look at the triangle I've drawn here with the red line and the two green lines, are there any special angles in this triangle? Where's the right angle? Yeah, there's a right angle right down here at home base, which means it's perpendicular. Those two lines are perpendicular. They meet at a 90-degree angle. And so we're going to use this famous theorem, Pythagorean theorem, in order to answer this question. So first we'll get somebody to remind us of what that theorem says, and then we'll give it a shot. Alexa, 3. Okay, so if I just say Pythagorean theorem, probably many of you just think that equation, a squared plus b squared equals c squared, and that's the conclusion, but we need to know what it applies to. It doesn't apply to like a rectangle, right? What does it apply to? What kind of a triangle? Is a right triangle. This theorem is only valid when we're thinking about a right triangle, a triangle with a 90-degree angle in it. And then the other important piece here is that the A and the B are the small sides and the C is the big side. The hypotenuse is the fancy word for it. So let's give this a shot. We'll go to the baseball question and we'll say that this one right here could be A. This one over here is B. It's totally okay to change the letters on those ones, but this guy right here is definitely C. And we need to make sure that C is the one that's opposite that 90-degree angle. Okay, A and B can be swapped, but C is always the one opposite the 90-degree angle. So according to the equation, we get a squared, which is 90 squared, plus b squared, b is also 90, so that's 90 squared, equals c squared, the magic number that we're looking for. Okay, and then we'll just clean this up a little bit. So 90 squared is 81 with a couple of zeros, plus another 8100, equals c squared. Smush these together. 16,200 is c squared. And then finally, what do we do to both sides? Who was that, Yurka? Square root. So take the square root because that's the opposite of this squared symbol. So c is the square root of 16,200. So with the calculator, we'll type this in, and then we'll round to the nearest tenth of a foot or something. 127. Good. So that's how far it is between third base and first base, about 127 feet and change. Questions on that? Okay, so the tip-off that we're going to be using this famous Pythagorean theorem is that you have a right triangle. That's when we use it. So let's try one more of these, and then we'll look at the exponent problems. Number 5, boo. Okay, so we've got this home entertainment unit and the space for the TV. So we'll just say that the home entertainment unit has these shelves down here, and we're trying to see if the TV will fit in the big space. And it says that this space is 17 inches by 21 inches. And we've got a 27-inch TV, and we want to know if it'll fit. Okay, so first, what does it mean to say that the TV is 27 inches? 27 inches on the diagonal. It's kind of strange. Maybe we take it for granted because we're just used to seeing televisions advertised by one number, but there are two natural numbers to give you for the size of a television, the length and the width, right? They don't give you either of those. They give you the one measurement along the diagonal. So if you have a 35-inch TV, go ahead and get a tape measure out. That's going to be how long it is on the diagonal. It's not the length or the width. From a marketing standpoint, can anybody explain why they tell you the diagonal? Okay, maybe it's cheaper to print just one number instead of two. It's a bigger number. What's the biggest way I could take a tape measure and put it up on this rectangle here? If I go vertically, I get 17. If I go horizontally, I get 21. But I can go bigger by some kind of, cutting across here through the middle, and the diagonal is the biggest thing you can possibly find. So, of course, they will advertise the biggest number that it's possible to find from that TV set. So, I want to know if the 27-inch TV will fit. What do I need to calculate for my entertainment system? The diagonal, right? We're just going to calculate how long this diagonal is, and then we can compare it to the 27-inch TV. So let's find the diagonal. So we'll go ahead and draw in diagonal. And we'll just point out it's a rectangle, so that's a right angle up there. Now the most important letter to identify is the C. Is the C 17, 21, or unknown? It's unknown. It's the one that's opposite the right angle, okay? And you can call the A and the B either of these numbers. The C is the really important one. Okay, so we'll use our favorite equation for today. A squared plus B squared is C squared. So that means 17 squared plus 21 squared is C squared. So 17 squared is 289. 21, 441. I think it's 730. $27.02. Questions on the process? So that 27.02 is the amount of space we have in our home entertainment center. So will the TV fit? We have a 27-inch TV. Yeah, I mean, it technically we just barely have enough space, and we better hope we didn't mismeasure anything. What's that? Yeah, that's right. Okay, we're good on the Pythagorean Theorem stuff. Again, what will you be looking for in your homework problems to know this is the right theorem to apply? Right triangle. That's what you need. If you don't have a right triangle, you can't use this. All right, so that's the Pythagorean Theorem stuff. Now we're going to shift gears and talk about exponents. Let me say this. So we're going to see rules of exponents on several different classes coming up. Today's just our first day talking about different rules or laws of exponents. And I will say that applying exponent laws are some of the trickiest problems for 096 students in my experience. Today, I think, is going to be relatively straightforward because you're going to be seeing rules that you've seen before. And it's a small collection of rules we'll see today, but as the collection of rules grows, it's going to be more and more tempting to apply the wrong rule to a certain problem. And so you really want to focus on thinking carefully about the rules today, even if they're easy rules today, just to make sure you know what's allowed, and maybe just as importantly, what is not allowed. All right, so it says many of the rules for working with exponents will follow naturally from the definition of an exponent, and here are some examples of exponents. So 7 squared, what does it really mean? 7 times 7, and that's 49, and that's easy. 5 to the 4th, what does that really mean? 5, 4 times. 5 times 5 times 5 times 5. And that's our 625. And then 2 to the 8th means 2 times 2 times 2, 8 of them. And that's 256. So just some vocabulary here. Exponential expressions are things that are written in the form x to the n, a number raised to another number. We call them exponential expressions because they have exponents in them. The number x is called the base, and n is called the exponent. So for example here, which number is the base in 2 to the 8th? Is it 2? That's the base. And I guess that means that the 8 is the exponent. All right, that makes sense. We knew that word applied to the power before. And the definition written out probably doesn't mean too much. You already know what something raised to a power means. You just copy that something the right number of times. Okay, and then it says understanding the relationship between exponents and multiplication is important in this and future math courses. So we'll start here with 7, the 5 laws of exponents below. So the first one tells you what to do if you have one exponential thing multiplied by another exponential thing. I'm just highlighting that the multiplication there is important. If there were an addition sign in between, it would not be this rule. So this is a really particular thing. And it turns out what you do is you copy that base, the x and the x get copied one time. And then what do we end up doing with the powers, according to the rule, is we add them. Now, it's not really something I want you to memorize. I'd rather you just think about it and be able to come up with it on your own. So for example, 3 to the 5th times 3 squared. Well, according to the rule, it's 3 to the 7, because the rule says you copy that base one time and then you add the powers, 5 and 2. But why does it work? Well, 3 to the 5th is really just 5 3s next to each other. And 3 squared is really just another 2 3s. And we're multiplying them all together. And what's a shortcut way to write down all that? Is 3 to the 7th, right? So I'm hoping this rule is very natural, right? It's something that makes sense. All right, next one is a division problem. So don't worry about what the rule says there, but let's just look at this example. How many 3s upstairs? 5 of them, so there they are. How many 3s downstairs? 2 of them, and then what happens? Forget this, but what happens to some of these 3s? 2 on the top, cross out. Right, so all the 3s on the bottom cancel. How many 3s are left over upstairs? 3 of them. And so the answer is just 3 to the 3rd. And was there an easier way to do this without writing it all out? So yeah, we had 5 3s upstairs, and we lost 2 of them because they canceled downstairs. So that's the 5 minus the 2, and that's what that says right there. It says you subtract those powers. Okay? And I just want to point out that we have seen all 4 operations in here. There's a plus, there's a minus, there's a times, there's a divide. But what we have not seen in here is something like x to the a minus, or sorry, x to the m minus x to the n. You guys agree? That is not in this list of 2 rules, right? So at the moment, if you were faced with like x to the 5th minus x squared, or we could even change it to a number, 7 to the 5th minus 7 squared, it might be tempting to say, oh, we take the exponents and we subtract them. And so we get 7 to the 3rd, right? It could be tempting to do that. It seems reasonable, but it's not true. And so you got to be really clear when you get to apply these rules. Even if the rules are believable with these numbers written out, you got to make sure you don't apply them in the wrong circumstances. These 2 rules only apply to when you have 2 exponential things multiplied or divided, that is all. So big old X through that. Okay, the next one is here. It's when you have some exponential thing raised to another exponent. So let's look at this example. 3 to the 5th squared really means 2 copies of 3 to the 5th. Yes? You don't need to write them all out because actually this thing is this rule, isn't it? Because you have 2 exponential things multiplied. So according to that rule, what are you supposed to do with the powers? Is you add them, and what do you do with the 3's? You just copy it. It doesn't become 9. It's not 3 times 3. It's not 3 plus 3. It doesn't become 6. It's just a single 3 raised to the 10th power. I wrote all the 3's out, but however you do it, you'll end up with 3 to the 10th. So was there a shorter way to do this, looking at just the numbers 5 and 2, to try to build a 10? What can you do? You multiply them. So apparently that's the shortcut, is when you see a power raised to another power, you get to multiply them. Notice that the answer is not 3 to the 5 squared. It doesn't become 25. We're multiplying these 2 numbers up here, that 5 and that 2, even though it kind of looks like the one is an exponent of the other. Okay, next rule here, number 4, says, well, what if you have a single power on the outside of a multiplication? So 2 guys multiplied together, all raised to a single power. Let's take a look at this guy. 3 times 4, all raised to the 3rd power. So what does it really mean? Well, it means you have 3 copies of 3 times 4, yes? And then I'm just going to regroup things. So I'm going to put all the 3's together and then separately all the 4's together. How many 3's do we have? 3. How many 4's do we have? 3. And so the whole answer is just 3 to the 4th, sorry, 3 to the 3rd times 4 to the 3rd. And so apparently what happens is that if you have 2 guys multiplied to a power, in some sense you can distribute, although technically that is not the right word, but that 3, that power, comes in and hits both of the guys in the parentheses. It becomes 3 to the 3rd times 4 to the 3rd. We would. So if we had something like this, x to the 4th times y to the 5th, the whole thing to the 7th power, we get to apply this rule, and this rule says that the x to the 4th and the y to the 5th both get what power? Both get a 7th power. That's what it says, right? That's what this rule says. It says when you have 2 things multiplied, all raised to a power, that power comes in and hits both of them. And now we have a new rule, one that we've just seen. What do you do when you have x to the 4th to the 7th? Which rule is that? It's the multiply rule. It's this one right here in the middle of our table. X to a power, the whole thing to a power. So this is really x to the what? 28 and then y to the 35. So boo, that's absolutely right. You bring that power in and you multiply it by what's there. Victor. They don't change at all. It's a good thing to think about because it's really tempting to make it x squared or to make this whatever we had before. It's tempting to make this single 3 into a 9 or something because we had 2 of them before. The base just stays exactly the same. Okay, and then the last rule is here in the bottom. Let's look at 3/4 cubed. It means you have 3 copies of that fraction, yes? And then how do you multiply? How do you multiply fractions? Do we need a common denominator? No, just go straight across. So upstairs is just 3 times 3 times 3. Downstairs, a bunch of 4s. And grouping stuff together, we just get 3 to the 3rd over 4 to the 3rd. And so it's another kind of thing where if you have power on the outside, that power comes in and in some sense distributes to the 2 things inside. So rules 4 and 5 are basically the same idea. Whether you have multiplication or division, powers on the outside come in and hit both of those things. Ooh, is there another question? If the 4 was a 3 in here? It would, but probably we could see that without going through all that detail because how much is 3 over 3? Is 1, and so we would know right away the whole thing would be 1. But yes, they would all cancel. Okay, so let's go on to the next page. Couple more rules, or I guess your book calls these properties of exponent as opposed to laws of exponents. So there are 2 rules in this table, and one of them we're going to look at today, and the other one we're going to ignore until next class. Let's just look at this first rule. It says a to the 0 is 1. Any number to the 0 power is 1. Any number to the 0 power is 1. So if you have a calculator handy, type in 5 raised to the 0 power. See what it says. So 5 to the 0. What did you guys get? Anybody else get 1? And what if it were 17 raised to the 0? What? It doesn't make any difference what number you put in there, except there's one little sticky point in that you can't put a 0 in. If you try doing 0 to the 0, I expect the calculator will explode. Let's see what happens. 0 to the 0. No, this one can handle it. Actually, I'm not really thrilled with that. I think that's a programming error. Let's try this guy. 0 to the 0. We get an error. So any number to the 0 is 1, except for this one little funny thing which you won't ever see. But it's kind of a strange rule. Any other guesses for what a reasonable answer might be for any number to the 0? Like it's apparently 1, but 0 seems like a perfectly good answer, a reasonable answer. So there is a reason that it's equal to 1, but it's kind of strange. You know, like, I mean, I know that 5 cubed means I have 3 of these guys, right? And 5 to the 1st means I just have a single one of them, right? But if it's 5 to the 0, it means I don't have any of them. And if I don't have anything, then 0 seems like a perfectly reasonable answer. But it turns out 1 is actually the right thing to do. And I can convince you of this. Suppose that we had this here, 5 over 5, no, 5 cubed over 5 cubed. Now, without doing any work, what's the answer to this problem? It's 1, yeah? Top and bottom are exactly the same. This is definitely equal to 1, no questions, right? But we did have a rule. If we're going to just try to naively apply our rules without really thinking about this, can you find the rule? It's on the previous page. 1, 2, 3, 4, or 5. Which rule is this? It's number 2, because number 2 tells you how to handle when you have division and it's exactly the same base. That 5 is exactly the same. So whatever the base is, it gets copied over here. And what do you do with the powers, according to rule number 2? We subtract them. So it's 3 minus 3, right? And so how much is that power? It's 0. So if 5 to the 0 is going to have any meaning, and if I need this rule right here to still be valid, where I get to subtract because there's canceling, then I have no choice. What do we have to define 5 to the 0 to be? We have to define it to be 1. So this is why it's 1. It's not 0. It's 1. All right. So we're going to ignore the rest of this table for today. Like I said, we'll come back to it next time. But let's try these ones here without a calculator. So the first, well, they all kind of look the same, actually. They're quite similar. So the first one is -4 in parentheses squared. I mean, I'm just going to put 16s through all of these. What's the only possible twist to the final answers? Yeah, positive or negative. That's the only question. So they're all going to be 16 of some flavor. So how about the first one? Is it positive or negative? It's positive because you are squaring that negative in there, right? This literally means take -4 and write it twice. And we know multiplying two negatives gives us a positive. You don't need to include the sign, but I'll put it there to stress that we finished it. Victor? It would give us what kind of an answer? That's right. What is this one equal to? That's good. 4 times 4 times 4 is 64. 3 negatives is the same as 1 negative. So there's definitely an even odd thing happening. Good point. How about this next one? This one's really easy to get wrong. A lot of people see this one as being the same as the first one. And so here's the question. The question is that 2 strong enough to reach that negative sign? Or does it only reach the 4? It's not strong enough. And the reason it's not strong enough, I'm going to put some invisible thing in here. This really means -1 times, right? You can think of a -1 of a 1 times in front of any number. And so we have 2 operations. We have multiplication, which was invisible, but it's really there, and we have an exponent. How do we remember what to do for the order of operations? PEMDAS, does that sound familiar? Okay, so P stands for parentheses. There aren't any. E stands for exponents, which means that exponent comes before the M, which stands for multiplication. So we do the exponent before we do the multiplication. So you don't get to even look at that -1 times. You're just doing the exponent, which is 4 squared. How much is 4 squared? 16. And then finally, we get to do the multiplication last. -1 times 16 is -16. So that's a really important difference. It's really easy to get that second one wrong. So take your time, get used to thinking about that invisible one. Okay, and then finally, the last one. So first thing to do is the exponent, which means this piece, which means that negative outside is just sitting there on the outside. How much is -4 squared? 16. And then there's a negative sitting in the front. So what's our answer? -16. This is the right answer. It is wrong to do this. I just copied the original. It is wrong to say, okay, that negative and that negative cancel. And so this problem is really just a positive and a positive 4 squared by thinking the 2 negatives next to each other cancel. Those 2 negatives, they appear next to each other, but that exponent takes precedence, right? It's a higher priority. So these 2 negatives don't have a chance to work together. So I'm going to put a big old X through this guy too. All right. Questions on those? Okay, so we've got almost 40 minutes. Go on to the next page, and there's a big old table of stuff you're going to fill in. There's an answer key at the bottom. On the next page after that, big old table of stuff to fill in, answer key at the bottom. And then finally, the third page of the group activity is 3-word problems all related to Pythagorean theorem. Raise a flag if you get stuck.